In the previous lecture, we have studied about definitions of volumetric ratios and weight volume ratios and their relationships based on two approaches. They are specific volume approach and unit volume approach. So, in this lecture, we will be trying to look into again the soil aggregate basic relationships using unit volume approach, and we will try to solve couple of problems, and then I will introduce to the mineralogy of fine grained soil particles. So, if we review that, we established different relationships among volumetric ratios and weight volume ratios, and we have also defined in the previous lecture. And we said that there are two approaches in the phase diagram method. One is the specific volume approach, in which the volume of solids is set as 1, unit volume approach where the total volume set as 1. So, in this lecture, let us look into the methodology of unit volume approach. So, in the unit volume approach, the total volume V set as 1, as the phase diagram method requires certain quantity of soil be specified. So, here the total volume is set as 1. Basically, the porosity N is used in place of void ratio here. This approach is used when no weights or volumes are given in the problem statement. So, one can select depending upon the problem statement. So, let us consider for the unit volume approach V is equal to 1 for a partially saturated soil, a 3-phase system where there are solids, water and air. On the right hand side you are seeing the weights, on the left hand side you are seeing volumes. So, when we set the total volume as 1, if you look into it, these weight of solids deduced as Gs into 1 minus n gamma W, and weight of water is weight of solids into water content. So, water content times Gs into 1 minus n gamma W, and weight of air assumed to be 0. With the definition of volume of voids as n, we can say that volume of voids is equal to n and volume of solids is equal to 1 minus n. By knowing the volume of water, by knowing the weight of water, we can say the volume of water is equal to Wgs into 1 minus n. Let us look the deduction of this particular figure from for a partially saturated soil 3-phase system. We know N porosity is equal to volume of voids to total volume. With V is equal to 1 in unit volume approach, N is equal to Vv. The volume of voids is set now as N. Then void ratio is equal to ratio of volume of voids to volume of solids is nothing but N by 1 minus N. So, from the previous deduction, gamma D is equal to Ws by V is equal to 1 minus n Gs gamma W by 1. Because of this, gamma D appears like 1 minus n into Gs gamma W. Gamma bulk, total weight divided by volume, is nothing but weight of solids portion plus weight of water divided by volume is 1. Percentage air voids can be deduced, Na is equal to volume of air to total volume, which is nothing but volume of water minus volume of voids minus volume of water divided by V is equal to n minus Wgs into 1 minus n. So, this is for the case of a partially saturated soil. We have deduced expressions for gamma D and gamma bulk and percentage air voids by using unit volume approach. Let us look for a completely saturated soil where gamma sat is equal to Gs into 1 minus n gamma W plus n gamma W. This is nothing but for a partially saturated soil, the solids which is 1 minus n is the volume of solids, n is the volume of water, which is nothing but volume of water, volume of voids. Then volume of voids times unit weight of water gives the weight of water, and weight of solids is Gs into 1 minus n gamma W. So, from the definition of water content, weight of water divided by weight of solids, n gamma w divided by gs into 1 minus n gamma w gives you relation w is equal to E by gs, and E is equal to wgs is a relation between water content, void ratio and specific gravity of solids. This is for degree of saturation is equal to 1. So, in a simple way we can deduce relationships by using unit volume approach. Let us consider for a dry soil. In the case of dry soil, when total volume V is equal to 1 and volume of voids is equal to n, which is nothing but volume of air, and volume of solids is 1 minus n. With this we can say gs into 1 minus n gamma w is again weight of solids. So, dry unit weight of soil is weight of solids divided by total volume, which is nothing but gs into 1 minus n gamma w. So, in this way we can use this unit volume approach to establish relationship between different volume ratios and weight volume ratios. Now, let us look into a problem by using this unit volume approach. As you can see in this problem, a saturated soil, that means that the soil with a two-phase system, all the voids are filled with water, has a unit weight of 18.85 kilonewton per meter cube is given. That means that gamma sat, the saturated unit weight of a soil mass was given, that is 18.85 kilonewton per meter cube, and a water content of 32.5%. The water content was given, which is 32.5%. So, we are required to estimate void ratio and specific gravity of the solids. Now, let us solve this problem by using unit volume approach, V is equal to 1 approach. So, by drawing the phase diagram for a partially saturated soil, this is nothing but voids which are filled with water. So, the weight of water is n gamma w, weight of solids is 1 minus n gs gamma w, that is ws is equal to gs vs gamma w, where vs is equal to 1 minus n, gamma w is the unit weight of water and 1 minus n is the volume of the solids. By knowing from the definition of water content is equal to weight of water to weight of solids. So, weight of water is n gamma w, weight of solids is 1 minus n gs gamma w. By using this we can write w is equal to n gamma w divided by 1 minus n gs gamma w. So, in this problem we knew water content is equal to 0.325 expressed as decimals is equal to n by 1 minus n gs. So, by using water content is equal to 32.5% and substituting here in this equation, we will get a relationship between porosity and specific gravity of the solids. Now, we can write gamma sat, the saturated unit weight of soil mass, is equal to weight of water plus weight of solids divided by the total volume, which is nothing but n gamma w plus 1 minus n gs gamma w. So, by knowing gamma sat is equal to 18.85 kilonewton per meter cube, substituting for gamma sat is equal to 18.85, we can solve by using the equation 1, substituting here in equation 2, we will get the weight of solids. So, from there we can solve now by using this unit volume approach the void ratio as 0.463 and volume of solids is equal to 1 minus 0.463, that is void ratio is equal to 0.86, that is E is equal to n by 1 minus n. Saturated weight was given as 18.85 kilonewton and per a meter cube of soil. That means that here weight of water is equal to 4.63 kilonewtons from the water content. So, weight of solids is equal to 14.22 kilonewton, that is what we have deduced previously. So, substituting the void ratio in the previous expression 1, that is in this, W is equal to n by 1 minus n gs, we will get the specific gravity of the solids as 2.65. So, what we did is that we tried to use the phase block method, in which we set total volume as 1 and we have used the given values in the problem and tried to deduce the asked parameters like void ratio and specific gravity of the solids. Now, let us look another problem by using specific volume approach, that is volume of solids is equal to 1. So, in this problem the problem statement is follows, the problem as follows: a sample of dry sand having a unit weight of 16.5 kilon per meter cube. That means that the given unit weight is dry unit weight of a given soil mass, and specific gravity of solids Gs as 2.7 is placed in the rain. That means that the dry sand has been placed in the rain. During the rain, the volume of the sample remains constant, but the degree of saturation increases to 40%. So, it is given that the degree of saturation increases to 40%. So, in that case, determine the unit weight and water content of soil after being in the rain. So, let us try to look into this problem and solve by using specific volume approach. So, given dry unit weight of soil mass gamma d is equal to 16.5 kilon per meter cube, specific gravity of solids is equal to 2.7 and degree of saturation as 40%. So, we are required to determine water content and bulk unit weight of soil mass. So, by using gamma d is equal to Gs gamma W by 1 plus E, calculate E void ratio as 0.636. This can be obtained by rearranging this as Gs gamma W by gamma d minus 1. So, substituting the respective values, we will get the void ratio. So, by drawing the phase diagram for this is a case of a partially saturated soil. Initially, the soil was in two phase system. After being placed in the rain, the water starts entering. So, the soil transforms into a three phase system. So, by drawing a phase diagram for a three phase system, here these are the solids and water and air. So, by setting volume of solids is equal to 1 and the rest as volume of voids is equal to void ratio is equal to 0.636, total volume is 1 plus 0.636. From volume of solids as 1, by knowing specific gravity of the solids, we can determine weight of solids as Ws is equal to Gs Vs gamma W, as Vs is equal to 1. By knowing Gs is equal to 2.7, we can write Ws is equal to 2.7 into 10 to 27 kilonewton. So, from the degree of saturation definition, fundamental definition is nothing but degree of saturation is equal to volume of water to total volume of voids. So, we knew that degree of saturation is 0.4, that is 40%. So, volume of water is equal to 0.4 times 0.636, which is set as volume of water as 0.254. So, we have obtained the volume of water, it is a component of the volume of voids, which is 0.254. By knowing the volume of water, we can determine the weight of water, that is 0.254 into 10 is 2.54, that is the weight of water. So, from the definition of water content, W is equal to weight of water to weight of solids into 100, we can get the water content for this given problem as 9.42%. The gamma bulk, the bulk unit weight of soil mass, that can be deduced as total weight to the total volume, that is weight of solids plus weight of water to the total volume, that is 27 plus 2.54 divided by 1.636, that is 18.05 kilon per meter cube. So, in this we try to solve a couple of problems by using this approach, and the similar problems can be expected and can be solved easily by using either specific volume approach or unit volume approach. So, before introducing the types of clay minerals, let us once again look the geologic process affecting the origin of soil deposits. As can be seen here, the source is igneous rock. After mechanical and chemical weathering, it transforms into residual soil, and this residual soil with the agencies it can get transported and deposited in other places and forms sediments, and these sediments after a process of induration form sedimentary rocks, and after a process of metamorphism the sedimentary rock transforms into metamorphic rock, then again into igneous rock, and a sedimentary rock can also directly transform to igneous rock. So, this is the basic cycle which continues. From igneous rock the residual soils are formed, and these residual soils can remain at that place, and otherwise the part of the soils can be transported either by using wind, water, other agencies to form sedimentary deposits. These sedimentary deposits with the process of induration can form sedimentary rocks, and these sedimentary rocks after undergoing a metamorphism can transform to metamorphic rock, and then after due course of time can transform to igneous rock, or a sedimentary rock can transform to igneous rock. So, that is what we have seen in the previous slide, the progression of mechanical and chemical weathering that converts all types of rock to residual soils, and these soils transport and deposition to form sediments, and the depositions to form sediments, and the eventual conversion of sediments to sedimentary rock through a process of induration. This is the process which affect the origin of soil deposits. And this slide shows a typical residual soil profile, a schematic profile showing the approximate parallelism in weathering zones. You can see a parent rock and a weathered rock and a residual soil profile. As discussed, this residual soil has the properties pertinent to the parent rock. Here in this slide below, a residual soil profile is shown derived from the volcanic rock in western Oregon, USA. Transported soil profiles, and these soils can get transported either by wind, water and other agency. So, as you see here, a parent rock, a rock and a thin weathered zone, and the transported soil deposit can be seen here. Note that the soil depth bears no particular relationship to rock surface topography, and the soil thickness varies according to the physical condition during the deposition. So, the soil conditions, soil thickness is varying according to the physical conditions during the deposition. This is a typical distribution of the predominant soil deposits in India, and this is a map showing different types of soils superimposed on the map of India. You see here this particular type of legend which indicates alluvial deposits, and these are the desert soils, and this portion, this particular portion here, and then here parts of Kerala, and here shown the laterites and lateritic soils, and here majority of the portion here shown, this particular one is black cotton soils, and the coastal belts you can see the different types, the soil, the type of soil which is marine soils, that is marine deposits, and the boulder deposits occur along this particular region here, and foot Himalayas and all is the boulder deposits. So, different types of soils, forms, complicates, necessitates the requirement for understanding the soil mechanics. So, before looking into the different types of mineral, the another important property we should look upon is the grain shape. We said that once the soil forms from the disintegration by chemical or mechanical weathering, it undergoes or it gets disintegrated into small particles. So, during the process of breaking, either due to mechanical weathering or due to transportation either by wind, water, other agency, it undergoes changes in the shape. So, the shape of the soil grains is a useful grain property in the case of coarse grain soils, and it is important in influencing the engineering behavior of soils. The shape of the soil grain is a useful soil grain property in the case of coarse grain soils, and it is important in influencing the engineering behavior of soils. The shape of grains in a coarse grain soil can be examined with the naked eyes. We also seen in the previous lecture different types of coarse grain soils like coarse sand and medium coarse sand, where the shape of the grain can be seen with the naked eye, whereas fine grained soils require microscopic examination. So, the grain shape is an important property for coarse grained soils. Generally, a general classification can be set for based on the grain shape: bulky grains or flaky grains or needle shaped grains. So, the based on the grain shape, they can be classified, the soil can be classified as bulky grains, soil grains can be classified as bulky grains, flaky grains and needle shaped grains. Bulky grains are soil grains where all dimensions of a grain are more or less the same. So, these are the characteristics of sand and gravel soils. So, bulky grains are soil grains where all dimensions of a grain are more or less the same. So, these are the characteristics of sand and gravel soils. Now, let us look. So, the source of this mechanical source of these bulky grains are mechanical breakdown of parent rocks. So, during the transportation either by wind or water, the sharp edges of grains may get worn out and the grains may become rounded. So, for example, river gravels and wind blown sands form rounded grains, rounded bulky grains. Alluvial soils, they form subangular to subrounded. So, the bulky grains, the source is the mechanical breakdown of parent rocks, So, during the transportation by wind or water, the sharp edges of the grains may get worn out and the grains may become rounded. So, for gravels which are found along the river beds like river gravels or wind blown sands like in dune sands, the grain shape will be rounded in nature. Alluvial sands, that is along the river deposits, subangular to subrounded shapes can have. The typical shapes of bulky particles. This slide shows a different shapes of bulky particles. Here you can see a subangular grain shape where edges distinct but fairly well rounded. This is a subangular shape, and these are two different types of angular bulky particles. The sharp edges in crushed stone or so can be seen here. Very rounded or subrounded and rounded bulky grains can be seen here. So, soils containing particles with high angularity tend to resist displacement and possesses high shearing strength compared to those with the less angular particles. So, as we said, the shape of the grain is very important for coarse grain particles. So, soils containing particles with high angularity tend to resist the displacement and hence possesses higher shearing strength compared to those with less angular particles. Let us look some photomicrographs of sand particles, and here this first picture on the left hand side which shows a photomicrograph of a beach sand, where you can see a contact here which is shown here. The contact between the different grain particles can be seen here, and here the photomicrograph of a quartz sand which is in the middle figure can be seen here, and the dune sand where the loss of contact because of the uniformity in gradation can be seen here. So, the important point to be noted is area of contact between grains is extremely small, and even small forces between grains produce very high contact pressures. So, area of contact between grains is extremely small. So, because of this, even a small force can induce very high contact stresses between the grain particles. Now, let us look the second type of the grains based on their shape is called flaky grains or plate shaped grains. These are mainly predominantly will be there in the fine grained soils, and they are the ones in which one dimension of the grain, namely its thickness, bears no relationship with other two lateral dimensions which are much bigger. So, the lateral dimensions are very large and the thickness is very small. This resembles a sheet of a paper or a leaf or a platelet. So, on the bottom corner of the figure, a submicroscopic crystal of clay minerals usually exhibit a flaky grain shape can be seen here. A flaky grain shape like can be seen here. This is a micro photograph of a kaolinite particle. So, the flaky grains are plate shaped particles. They are the one in which the one dimension of the grain, namely its thickness, bears no relationship with the other two lateral dimensions which are much larger. So, they resemble like a sheet of a paper or a leaf or a platelet. The other shape we defined like needle shaped grains. The one dimension of the grain is fully developed and is much larger than the other two dimensions. So, in this slide a photomicrograph of a clay mineral attapulgite is shown here, where a needle shaped grains can be seen here. There is a needle shaped grains are the characteristic of the clay mineral attapulgite. So, what we seen from this discussion is that the different shapes of grains, we have got rounded, sub-rounded, angular or subangular grains for bulky particles, and some flaky particles, flaky grains have got plate shaped particles or platelet particles, and needle shaped grains, that is one dimension of the grain is fully developed and is much larger than the other two dimensions. So, one thing important to be noted is the different shape of grains for soil can be noted. So, let us now try to look into the mineralogy which influences the soil behavior, like the properties of very fine soil fractions. So, the most important grain property of fine grained soil materials is the mineralogical composition. The most important grain property of the fine grained soil is the mineralogical composition. If the soil particles are less than about 2 microns, that is 0.002 mm, the influence of the force of the gravity on each particle is insignificant. That means, the surface charges overcome the weight gravity forces here compared with that of the surface charges. The influence of the force of the gravity on each particle gets insignificant. So, the colloid particles of soil consist primarily of clay minerals. The colloid particles of a soil consist primarily of clay minerals. The colloidal state is nothing but in the particles in which the domination of the surface charges takes place. So, the colloid particles of soil consist primarily of clay minerals. So, before defining clay mineral, let us define a mineral. A mineral is a naturally occurring chemical element or a compound formed by a geologic process. Classification of minerals based on the nature and arrangement of atoms can be in the following ways: carbonates, phosphates, oxides and silicates. Most of the clay minerals form in soil mechanics by using two abundant elements in the earth called silicon and oxygen. So, most abundant and important mineral is silicates. It was reported that 90% of the soil predominantly has silicates. So, the most abundant and important mineral is silicates, which is, as far as soil is concerned, which is very important. Two elements like silicon and oxygen. So, these silicon and oxygen form a silicates. The silicates are nothing but a group of minerals with a structural unit called silica tetrahedron. So, a slide here which shows oxygen at the corners of a tetrahedron and a silicon at the center. A central silica cation is surrounded by 4 oxygen anions one at each corner of the tetrahedron. So, this is called a silica tetrahedron, silica tetrahedron. So, several silica tetrahedrons link up in hexagonal pattern to form tetrahedral layer. So, several silica tetrahedron units link up in hexagonal pattern to form tetrahedral layer. So, this tetrahedral layer is represented by silicate sheet. It is called silicate sheet. It is represented like this. So, here the hexagonal network of tetrahedra forming a silicate sheet can be seen. You are seeing now a different silica tetrahedron units forming silica tetrahedral layer, that is a tetrahedral layer, that is silicate sheet can be seen here. So, the hexagonal network of tetrahedra forming a silicate sheet is shown in this particular figure. The another fundamental unit which forms by using aluminum or magnesium and hydroxides is the octahedron. So, in this slide another fundamental unit is shown, aluminum or magnesium at the center, and which is surrounded by hydroxides or oxygens. So, octahedron units link up to form octahedral layer. Octahedron units, so several octahedron units link up to form octahedral layer. If the anions of octahedral sheet are hydroxides and 67% of the cation positions are filled with aluminum, then it is called gibbsite sheet or alumina sheet. It is indicated with this particular shape. So, if the anions of octahedral sheet are hydroxides and 67% of the cation positions are filled with aluminum, then it is called gibbsite. If the cation positions are filled with magnesium, then it is called brucite sheet. But several clay minerals form with the combinations of silicate and gibbsite sheets only. In the a figure below here shows the structural network of octahedra forming an alumina sheet. Structural network of octahedra forming an alumina sheet with the combination of different octahedron units linking up to form octahedral layer or a gibbsite layer or alumina layer can be seen here. So, having defined the fundamental units and they become the source for forming the clay minerals. So, let us try to define now a definition of a clay mineral. We have already given the clay mineral is a constituent for the fine grained soil, where the clay mineral which is defined as chemical weathering which may result in the formation of a groups of crystalline particles of colloidal size for the particles finer than 2 micron, that is less than 0.02 mm, is basically defined as clay minerals. So, in the previous formation in the previous slides we have seen how the silicate sheets and gibbsite sheets can be evolved, and these silicate sheets and gibbsite sheets join together to form fundamental sheet structures, and they form different types of clay minerals. So, this is basically a silicate sheet and this is a gibbsite sheet or an alumina sheet. So, the three basic clay minerals are kaolinite, illite and montmorillonite. Kaolinite generally occurs in is prevalent in sedimentary and residual soils. Kaolinite is generally prevalent in sedimentary and residual soils. Illite common in stiff clays and shales as well as in the post glacial marine and lacustrine soft clay and silt deposits. So, illite another mineral which is common in stiff clays and shales as well as in the post glacial marine and lacustrine soft clay and soil deposits. Montmorillonite is the third mineral, is a dominant clay mineral in some clays and shales and in some residual soils derived from the volcanic ash like bentonite. Other minerals which are there, some forms halloysite, chlorite, attapulgite and alophane. So, in this slide we have seen different clay minerals. So, let us discuss one by one about the different clay minerals, like three important clay minerals which will be introduced in this particular lecture, which is kaolinite, illite and mantomolite. As discussed, the kaolinite basically form with the repeating layers of one silicate sheet and one gibbsite sheet or alumina sheet. So, here the elementary layer of kaolinite is shown. A gibbsite sheet or alumina sheet is strongly attached to a silicate sheet. So, the repeating layers of alumina and silicate sheet forms kaolinite layer. In this here in this figure, kaolinite layers join to form kaolinite particles is shown here. So, here as you said, a group of silica tetrahedrons form silica sheets, a group of octahedrons form alumina sheet, and these two get attached through a bonding forms elementary layer of kaolinite. Several elementary layers of kaolinite form a kaolinite particle. So, kaolinite particle basically the elementary layer is 7.2 angstroms thick. 1 angstrom is equal to 10 to the power of minus 10 meters. So, kaolinite is basically a repeating layers of one silicate sheet and one gibbsite or alumina sheet. Is also called kaolinite is also called 1:1 clay mineral. That means that one silicate sheet and one alumina sheet forms an elementary layer of kaolinite. So, here the nature of bonding in kaolinite elementary layer is shown. How the silicate sheet and alumina sheet are attached is shown in this slide, and this is a alumina sheet and this is silicate sheet. So, a kaolinite crystal or a particle then consists of stack of several layers of the basic 7.2 angstrom thick layers. So, here the typical kaolinite particle has width length equivalent to 1000 to 20,000 angstrom units, and its thickness is 100 to 1000 angstrom units. So, this kaolinite particle is formed typically by 70 to 100 elementary layers, that is each elementary layer has got 7.2 angstrom thickness, forms approximately 100 to 1000 angstrom thick particle. This forms strong hydrogen bonds between the hydroxyls of gibbsite sheet and oxygens of the silicate sheet. Because of this particular nature of bonding, there is a little tendency in the interlayers to allow water and to swell. So, kaolinite has got less affinity for water and has got a little tendency in the interlayers to allow water and to swell. So, a kaolinite crystal or a particle then consists of a stack of several layers of basic elementary layers. Generally, in a kaolinite particle about 70 to 100 elementary layers will be there, and the kaolinite particle is reasonably large with dimensions one of the lateral dimensions ranging from 1000 to 20,000 angstroms and thickness 100 to 1000 angstroms. There is a strong hydrogen bond between the hydroxyls of the gibbsite sheet and oxygens of the silicate sheet, and this forms and this shows a little tendency in the interlayers to allow water and to swell. Here the photomicrograph of kaolinite, and these photographs are obtained from the scanning electron microscope, that is called SEM, scanning electron microscope. Here a cluster of the plates can be seen in a kaolinite particle, where this resembles pages in a book. So, you can see the stacks of plate shaped particles in a kaolinite particle. So, this photograph shows the scanning electron microscope photomicrograph of kaolinite. So, it presents the cluster of plates resembles pages in a book. And as we said, another mineral which is mantomolite mineral, this is called 2:1 clay mineral and is also known as smectite. Pure seams of mantomolite can exist in Wyoming bentonite in Australia. Pure seams of mantomolite can be there in Wyoming bentonite. So, this mantomolite is 2:1 clay mineral because two silicate sheets sandwich one alumina sheet or gibbsite sheet. And because of this, one alumina sheet and two silicate sheet form the elementary layer in case of mantomallite, and these elementary layers are separated by several water layers and cations, which get separated because of the weak van der Waals forces. Because of the weak van der Waals forces between these two elementary layers, the spacing between silica and gibbsite and silicate sheets depend upon the amount of water available to occupy the space. More amount of water and then more will be the spacing. Generally, they can even get extended up to 400 angstrom thickness. Each elementary layer can get separated into 400 angstrom distance. This is because of the weak bonding due to weak van der Waals forces, and this mineral is predominantly will be there in black cotton soil, is one of the transported soils we have introduced earlier. So, in this figure is several layers of alumina sheet and a silicate sheet is shown here. And here the nature of bonding in mantomallite elementary layer can be seen here, where alumina sheet is sandwiched with the help of silicate sheet and another silicate sheet at the bottom. So, is presented here alumina sheet or gibbsite sheet and a silicate sheet at the top and silicate sheet at the bottom. This is the nature of the bonding in case of a mantomallite elementary layer. So, this slide shows photomicrograph of mantomallite, where among the clay minerals, sodium mantomallite, that is predominantly the cations here are sodium, sodium mantomallite, has the smallest and filmy particles. So, you can see the gel type appearance of the photomicrograph for the mantomallite can be seen here. The approximate mantomallite particle has sizes from 1000 to 5000 angstrom units, and its thickness is only 10 to 50 angstrom units. 1 angstrom unit we said as 10 to the power of minus 10 meters. So, among the clay minerals, the mantomallite, sodium mantomallite has the smallest and that is very tiny particles and has got filmy particles, like gel like appearance can be seen from this the photomicrograph of mantomallite. The third clay mineral we introduced today is illite. Illite is nothing but repeated layers of gibbsite sheet sandwiched by two silicate sheets. It is similar to mantomallite except that the adjacent silica layers are bonded with potassium ions instead of water. So, these potassium ions bond the two negative surfaces of silicate sheets tightly. With that, it has got less affinity for water than kaolinite, and as well as more affinity for water than kaolinite, than less affinity for water than mantomallite. So, illite is nothing but a slide, a picture here which shows the elementary layer which is similar to mantomallite, one gibbsite sheet sandwiched between two silicate sheets. The only difference is that the water layers are replaced with potassium ions, and these potassium ions hold these silicate sheets tightly with an ionic bond. So, with this the potassium ions bond the two negative surfaces of this elementary layer to form to prevent any ingress of water. So, the particle size of illite are reasonably smaller than larger than mantomallite, slightly smaller than kaolinite, where 1000 to 5000 angstrom is the lateral dimension width and thickness is 50 to 500 angstrom units. The swelling potential of illite will be greater than kaolinite, but less than mantomallite. So, if you look into it, the kaolinite clay mineral has got larger particle size than illite, illite and montmorillonite, and the swelling potential of montmorillonite mineral is very high compared to illite and kaolite. So, that is the reason why the soils contain montmorillonite exhibit high shrink swell characteristics, and the soils containing 100% or 85% montmorillonite also used very widely in the soil engineering construction for supporting the boreholes, etc. So, in this lecture we try to understand about the unit volume approach and then its application for establishing relationship between weight volume ratios and volumetric ratios. And we also seen the importance of grain shape and different grain shapes like bulky shape, flaky shape and needle shape. And we also tried to introduce different types of clay minerals. Basically we said that 3 clay minerals will form with the fundamental units silicate sheet and gibbsite sheets. Kaolite forms with 1 silicate sheet and 1 gibbsite sheet. That is the fundamental unit which forms, we have seen that different structures of kaolite clay minerals and illite mineral and montmorillonite mineral. And we also discussed about the influence of this mineralogy on the properties like swelling potential and its particle size, etc.